will be, it can be made in an equation by different ways. It will be LW plus, yeah, another constant. I will call it L0, L0. So here, sorry, it's LC, it's equal to L0 plus LC, it's equal to L0 plus LW. Now if I increase the number of turns by 2 times LW, it will be 4 LW. You have LW, it will be 2 LW, and since it is from this side, it will be increased by 2 times. Of course, in the other side, it will be increased by 2 times also. So it will be 4 times. This equation is not correct, and I will explain later on. So now if you increase, now if you continue the calculation, if you increase the number of turns by n times, so the magnetic field Hn, it will be equal to m times n1, and it will be divided by 2 m LW plus L0. So this is the equation of the magnetic field when you increase the number of turns by m times. Now let's suppose that m tends to infinity. Now we increase to, because this scaling law that have been proposed by Manichtala, it's general. It's not limited for a range of power. It is general. It's a law. It can be limited by any condition. So let's now increase m to infinity. What will happen now? So if we increase m by infinity, then this one L0, it will be small. This one, it will be neglected. I will write here m tends to infinity, and then Hn, it will be equal to this L0, it will be neglected, and it will be equal to here the magnetizing current Im1. It will be equal to N1 Im1 over 2 m LW. So here you can see it's equal to H1 over 2m. This is wrong. Why it's wrong? Because if it is correct, oh sorry, this one, it's equal to N1 Im1. So we have to, if m tends to infinity, then we have also to simplify by m, and we will only get N1 times Im1 divided by 2. So it will be more or less equal to H1 divided by 2. This is not correct. Why? Because if B1 it is divided by m, then H1 also it should be by the same it should be decreased by the same factor. So what's the mistake? With the mistake, it's clearly and obvious, and you can determine it by intuition. It is Im1 here. We have, it should be also, it should change it also, because the magnetizing current and the magnetic field, they are also dependent. If the magnetic field is reduced, the magnetizing current also it is reduced. The magnetizing current is not only related to the voltage through the Faraday's law, but also it is related to the magnetic field through Ampere's law, and this relationship between the magnetic field and the magnetic flux density B equal to mu h should be always conserved and correct, otherwise the transformer it will not work. So what's the question, what's the how to we can correct this? So here it will be divided by 2, and also here you will converge also to divided by 2m, and you will converge also to the solution here, the correct solution. It will be Hn equal to h1 over m. So the correct solution for hn, or the correct answer and equation for hn, it's h1 by divided by m. So this is the correct answer. So now you can see that this relationship, it is always conserved, and the transformer, it will work. Now how we can calculate the inductance now? It is very easy. So we need to replace this n by mn square, and this LC also by the factor, or how much it increases when we increase the number of turns. So the right answer for Lm, you will find that it is equal to Lm m, it will be equal to m over 2 Lm1. So this factor 1 over 2, it might change depending how you calculate the relationship between LW and L0. Here I am not very accurate in my calculation, but you might find another factor, but it is when m tends to infinity, that factor, it will not affect the relationship. But you can see that in general, that the magnetizing inductance, when we increase the number of turns, it will be proportional to that factor, and it is not equal, as it is said by the scaling law of Manichtala and Nikola, that it will be dropped by n or by m when we increase the power by m. So here it is clear the result, and it is very clear when we increase the power, the magnetizing inductance, it increases. This is clear if you look to the magnetizing inductance of the power transformer, it's in the order of millihenry. But if you look to the transformer in power electronics, it's always in the order of microhenry. Now if you increase, if you move the number of turns, for example you have 10 turns and you increase it by 100 to meet with the voltage at high power, then of course your magnetizing inductance, it will increase to the order of microhenry, and this is very reasonable and logic. It's not the same as it is given by the scaling law of Mr. Manichtala and Nikola. I hope that the answer is clear. Next time I will explain what happens to the inductance when the current it increases, and this question, it is also posted in LinkedIn. I hope that now the answer is clear, and I will also be happy to receive also your comments and also your feedback. And thank you very much for your attention.